Alright, let's do a little review. So fun. For 3? 1, 2, yeah, I guess it is for review for number 3. Alright, we have an object moving in uniform circular motion in a horizontal circle. The mass of the object is 10. Nice. The angular speed is 70 RPM, revolutions per minute. Sketch the velocity and acceleration for each point. Okay, let's only worry about the ones that are labeled. How about that? They're all because I've got less room than you have. Alright, so A, which way is A going? I guess it doesn't tell you which direction. I'm going to go counterclockwise because retro-rotatory is what the cool kids do. So that's your velocity. This is going to be your velocity at B, and it'd be the same for all the points. I don't want to draw all of them. Your acceleration is going to be pointed towards the middle for both of them. Ta-da! Check. Calculate the speed in radians per second. Don't worry about that one. We're not doing that yet. Calculate the linear speed, magnitude of the tangent body in meters per second. Okay. So let's see here. If we've got 70 revolutions per minute, alright, that means if we, you could do 1/60th of that per second. So 70 times, divide by 60, come on, is equal to 1.617 rev per second. Now each revolution covers a radius of 20 times the circumference. So circumference is going to equal 2 times pi times r, which is 20, so times 40 pi, enter. So each second you are going to be moving 40 times pi, which is a big number. Anyway, it's going to be 146.6 meters per second. Ta-da! And that's your speed. Now, ta-da! If the centripetal force suddenly went to 0 at point A, sketch the path the object would take. Well, just keep going a straight line. Just be going like that. Ta-da! Next one. Oh, whatever. Check. Calculate the centripetal acceleration in meters per second per second. Alright, centripetal acceleration, same thing as force without the masses, equals v squared over r. V squared is 146.6 squared over the radius of 20. So that's squared divided by 20. So you're going to get 1,074. A equals 1,074.7 meters per second squared. Ta-da! Check. Calculate the centripetal force in newtons. Right? Well, we're going to use F is equal to ma. Have you ever heard of that formula before? So M is 10 times A is 1074.7, and you're going to get 10747. You could put another decimal if you want, whatever, I don't care. Newtons. Check. Sketch the centripetal force vectors in points A and B. Right there. FC, FC. They're the same as the acceleration. Cool. Let's do the next one. I'm not going to do all of them, but we're going to do half of them or whatever. We can do more by request, but you have to send it in. What is the maximum speed on which that many car radius can round a turn with the radius of this on a flat road? The coefficient of friction between the tires and the road is there. Hey, so it's like the banked turn problem without the bank, which makes it super easy. So we've got a 70-meter radius. We want to know what the speed is. V is equal to question mark. Alright, the car is on a flat road, which means it's got a mg of 1050 times 9.8, even though it doesn't matter. That's fine, it's fine. 0,290 newtons. So it's got a normal force of 10290 newtons. Right? Now if it's turning to the left, that means your frictional force is going to be pulling it to the left. Okay? So your friction force is 0.8 times that. which is 8232. 8232 newtons, right? So this is going to be your centripetal force, right? Fc is equal to your force of friction in this case, because the friction is pointing towards the middle of the circle. So mv squared over r is going to equal 8232. Now you could have set this up better, you know, done this all at once or whatever, but you know, just trying to do it the way you might do it. So I know what the mass is, so v squared is what we're looking for, is equal to 8232 times r divided by m. So this times r is 70 divided by m, which is 1050, is equal to v squared is equal to 548.8 to the square root, and you're going to get 23.4. Surprise, surprise, it's almost like the answer was written. Oh, wait, it was. Okay, so that's how you do that one. Hopefully it helps. Jumping to number trace here, a coin is placed 11 centimeters from the axis of a rotating turntable at a variable speed. When the speed of the turntable is slowly increased, the coin remains fixed on the turntable until a rate of 36 RPM is reached, at which point the coin slides off. What's the coefficient of static friction between the coin and the turntable? Alright. Man, you even vinyl, bro. So there's that. So this is 11 centimeters. I'm just going to change it to meters right now, which is 0.11 meters. Okay, we don't know. Oh, we do know this. Well, we have to figure out the speed. So let's figure that out real quick. So 36 revolutions per minute. Okay. So I want to know meters per second, so there's 60 seconds per minute. And then I know that each revolution has 2 times pi times the radius meters. So that'll change that. So 36 divided by 60 times 2 times pi times 0.11. So that means it's going to be traveling 0.414 meters per second. Okie dokes. Ready. So then, here's the coin. This is going to be mg. This is going to be also mg as your normal force. And here's your force of friction, which is mu mg. Alright. So that's its speed, so we know that the Fc is going to equal Ff, right? So Fc is going to be mv squared over r is going to equal mu mg. Cross out the m's because they go away. V squared is going to be 0.414 squared divided by r, which is 0.11, and that's going to equal mu, which is what we're solving for, times 9.8. Alright, typing this in, this number squared divided by 0.11 divided by 9.8, so we're going to get 0.16 mu equals. Ta-da! No units because it's coefficient of friction. Hey, that's the same thing that I got. Alright, hopefully that helps. Another one. How fast can it spin? A ball of mass half is attached to the end of a cord with the length of, whose length is 1.5 meters. Alright, this is 0.5 kilograms. 0.500. If the cord can withstand a maximum tension force of 50 newtons, what's the maximum speed the ball can have before the cord breaks? Hey, so the 50 newtons is going to be your centripetal force, right? So 50 newtons is going to equal mv squared over r. This is an easy one. So 50 is going to equal 0.5 v squared over 1.5. Quick maths here. 50 times 1.5 divided by 0.5, enter, square root, enter. So you're going to get about 12.2 meters per second. Hey, that's the same thing that's written there. Alright, I think this is the last one. This is I wanted to put one of these on here because Who doesn't enjoy one of these? An engineer, not that kind, wishes to design a curved exit ramp for a toll road in such a way that cars will not have to rely on friction to round the curve without skidding. Hey, do you know what that means? Do not have to rely on friction. So that means you have no friction here. To round the curve. Suppose a typical car rounds the curve with 18.4 meters per second. And the radius of the curve is 50. At what angle should the curve be banked? Nice. Draw a picture. Oh, I already have a picture, but I want to draw my own. mg. We don't know what theta is. So this is going to be mg cosine theta. mg sine theta. Normal force, but we don't care because there's no friction. Here's your centripetal force, Fc. That's the theta, so this is going to be your Fc cosine theta, and it's going to equal this one. These two are going to be equal to each other because there's no other forces that go that way. So Fc cosine theta is going to equal mg sine theta, divide by cosine, and then I'll do mv squared at the same time. V squared over r is equal to mg tan theta. Cross out the m's. Kick the g over. I'm just going to do that. I'm cheating a little bit. That's fine. Okay, so v squared over GR. V is 18.4 squared divided by 9.8 divided by the radius, which is 50. So v squared over whatever that stuff is equal to 0.69. Nice. It's equal to 10. So we're going to do the arctan, and you're going to get 34.6 degrees. Hey, that doesn't match. Oh, well, maybe can't trust them all, I guess. Maybe they put friction on there. Oh, well. Anyways, that's that. Hope you had fun. Let me know when you're panicking, and then we'll see you later.